All right, so now we're going to look at different ways to integrate these extended parameters into various workflows. To do that, we're going to use the Dynabead stimulated T cells as an example, and we're just going to look at each of these three populations in turn to see different ways that they can be integrated, or that the extended analysis parameters can help further resolve them. If you remember, we were able to take this very messy sample and separate out the beads from the cells and debris from the beads and cells that are interacting, well, bead cells and debris. So looking at those populations, we have beads, beads and cells, cells and debris. And I've already put in our quality control gates. Here I have everything backgated onto a density plot. As you can see, the beads are in a pretty standard and uniform area. And that's opposed to the beads on cells, which are spread out throughout the entire plot in the cells and debris. So we're going to start with how to quantify beads on cells, beads, because that is the most straightforward application. As long as you're working with beads that are a standard size, around 5 microns or larger. So I would use a histogram, area square microns, and set beads as my parent gate. Because beads are the standard size, we can predict how or where we are going to find singlets, doublets, and triplets. And actually, let me just expand this gate so we can look at the triplets. And so all I'll do to get this quantified, or get the quantification of beads, is add this gate, triplets beads, and we see here that's all that is contained there. Our doublets, and then our singlets. And all I have to do to export this is add a statistics box and just save that statistics box. And you can see over here, I have my counts, triplets, doublets, and singlets. So that's an extremely useful function, and it allows us to quantify how many beads are left so long as they're not interacting with any of the other events in the sample. As you can see with the beads on cells example, and let me backgate that again. With the beads on cells, they are spread out throughout the entire region. All right, so now let's look at how we might quantify our cells from our debris. One of the challenges with this particular sample is that it is such a messy sample with so many dead and dying cells and so much other debris in here that we aren't getting a clear resolution from the live dead. So if I come in here, see, there's no versions here where I have a clear peak. Oh, let me go to cells and debris that I feel necessarily extremely confident about gating on. And so while these are definitely not healthy, so are these. And even in here, I still have debris. So the way that I would approach this is to first clean up the sample and try to separate out the cells. And we are going to use a parameter that is also very useful for identifying interactions between events versus coincidental events. So we'll use this same parameter twice. So minor major ratio percent. You can even go to and then also eccentricity percent. And if I came in here and I just wanted to, let me make this a little smaller so it is a little easier to see. And if I come in here and I just draw a gate for us to just look at what is going on in this sample, we can see here we have our individual events, 1 or 2 interactions, the cells on beads, but overall most of these are cells or isn't too much debris, as opposed to the further that I move left. The less healthy everything looks. So cells and debris here. I am probably going to set a threshold around 50 and just eliminate everything upstream. Something else that is very useful is the area and the size parameters, because we know that anything that is significantly large or significantly small is not going to likely be a healthy whole cell. So we can look at the area square microns, but we can also look at the perimeter. So either of these would work. I'm just choosing perimeter because it's a little easier to see. So if we look down here, we can see these are dead cells for the most part. There's still a lot of debris. But as we come up here around 50, that's where we start to see our population of healthy cells. And anything that's here on the high end of the scale is almost certainly debris. And the same is true for area. And because these cells are a relatively uniform size, or they should be, I can just gate out a significant amount of unwanted events just using one of these features based on what I know about morphology. So we'll go ahead and we'll look at one more, circularity. And circularity is one of the parameters that is actually very uniform between sample types, as long as you are working with immunological samples and are typically round cell type. So if it's cell types round in suspension. Circularity below 80 is almost never, I've never seen those healthy, viable cells in human immunological samples unless there's cancer cells. And so for the most part, I would exclude just about everything below 80. So I'm just going to set my thresholds here. And we can see that we actually clean this up quite a bit. And a way to prove this to ourselves is to come up here and let me change this to a density. Oh. And I'm just going to draw a very messy polygon gate to gate out the debris. And if we set that as our parent gate, you can see the sudden shift in the events that have been excluded, and most of these below 80 are definitely not healthy cells. So higher circularity tends to be healthy cells. We can do the same thing here. Notice how the range changed and everything shifted, so up below 50. And if we shifted back to minor major ratio percent, we see the same thing, where everything is more or less above 75. So I can just pick this, pick one of these. In this instance, I am going to use circularity. And so this is my circularity gate. And now I have a really nice resolution between these two peaks. Oh. There we go. We're using Cytox Blue, I believe. So here, my dead population, 588, and my live population. And so contrast this with what we would have been working on with if we, not doublets and beads, cells and debris, if we were just gating with cells and debris for live dead. So by cleaning it up, we've gotten a much more reliable quantification of our cells, and that was just using circularity and then our live dead dye. So we can quantify beads, we've quantified our live cells. And the way I would save this is I would add a statistics box. And now I have all my counts saved, and I could just export that. And so then the final example that we will use this for are differentiating between interactions, between events, so cell-cell interactions, cell-bead interactions, and events that are just coincidental. So let's come here to the experiment workspace. I'm just adding a new one, and we're going to use a lot of the same parameters to do this. So one of the challenges when we are looking at interactions and complex samples is determining what events are coincidental. So they simply happen to be in the flow stream at the same time and so appear in the image together. So I would call this a coincidental event versus interactions. And so I would potentially call this an interaction here, interaction, interaction. And separating these is very challenging without imaging. And even with imaging, it would be tedious to do if we didn't have these parameters. This is a very small population. So we're going to really reduce the resolution on my histogram. And there are a few different ways that I can go about doing this. So one of the things I'm going to do here is I'm going to use my particle count feature. If we look in R1, this is where we're seeing a lot of these cell bead interactions compared to the singlet gates. This software is pretty good about identifying a cell and a bead and counting them as two events. So I'm just going to narrow this down a bit for myself too, and this is a way for me to double check how my gating strategy works. And so we can see cell and debris, 556, versus singlets and doublets. And I'm going to draw a singlet gate just to check what I'm excluding. So let's look at the singlets. So you can see in the singlet gate there's only about 60 events that could be cell bead interactions. There's 1, 2. I would not include these because they are almost certainly not statistically significant. But for argument's sake, we can keep it singlets and doublets. It'll just make it a little more complicated for now. But normally, I would only proceed with the doublets. So let me change this back to parent gate. Coming in here, cells, beads, and debris. We're going to first look at our circularity percent, and just notice that these low circularity events are coincidental rather than interacting. And as we shift up, now we're starting to see the interactions. This is also true as we come in here to eccentricity. And events with the low eccentricity are more of our interactions as opposed to our coincidental events. So I'm just going to choose a threshold. And I think around 75 is probably good, 75 to 25. And then I'm going to plot this against my live dead. BL2? No, BL1. And so let's look at that as opposed to our cells and debris. I'm actually going to copy this and compare in our group workspace over here. And this is nice. You can paste between these different categories. So let's look at live cells. Beads and cells. So this range, I'm just checking where the live range is, 275 to 7697. So based on the live dead gate that we've already identified using that same range, you can see 275, 7697. We've got about 400 cells that are still attached to beads. And we can refine this further using some of the other parameters such as area. We can eliminate some of these really small events and ultimately keep on going to get a more exact count. At this point, around 400 is exact enough for the work that I do. But this is just a great example of how many different ways that we can use these parameters to improve both sample prep and standardization. I would potentially set these thresholds and just refer back to them between preparations and be able to accurately and reliably assess my own preparations and improvements day to day and verify if there's something in the process that I'm doing that is shifting compared to somebody else. So these are just a few of the applications. And then don't forget that there's also the singlet gating that is very useful and is good for the rare events because it helps you eliminate anything that are doublets that are double positive because they're doublets as opposed to actually being cells.